So today we're going to talk about the finite element technique. And I guess we're going to start by just defining the actual problem statement that we're going to solve and go through some of the process of developing the actual solution technique. So here's our computational domain. We're going to do a 2D transient problem. So everything inside of here is our computational domain, and there's the boundary. One of the nice things about the finite element technique is that the boundary can be irregular with not any more difficulty. The partial differential equation we're going to solve is d dx of k dt dx plus d dy k dt dy plus g triple prime equals rho c dt d time. So conduction terms is generation, and that's storage. We need boundary conditions. So along the boundary, if I do an interface energy balance, I have potentially at least some heat flux, specified heat flux, some convection, so H times T infinity minus T. And then if I define a direction normal to the boundary, the temperature gradient, that direction has to be consistent with carrying this energy away by conduction. So that would be minus K times dt dN, where N again is a normal outward vector. Alright, so my boundary condition then is all the way along this boundary. I would have minus K dt dN equals Q double prime S plus H times T infinity minus T. And then the last thing I would need is an initial condition. So the temperature at time equals 0 has to be some specified function of x and y. So we're going to use the Galerkin weighted residual technique, which means that we're going to take this partial differential equation and use it to define a residual that would be equal to 0 in the case where we were substituting in the exact solution, but in the case that we substitute in an approximate solution, we will get a residual, and we're going to make the weighted residual, the weighted average residual, equal to 0. So let's start by just defining residual. So the residual for this equation would be rho times c times dt dx, dt d theta, so that's this term, minus everything over here, so minus d dx of k dt dx minus minus d dy of k dt dy minus g triple prime equals 0 if these are all the exact solution. Right? If I substitute in my approximate solution, I get rho times c times dt d theta minus d dx of k dt dx minus d dy of k dt dy minus g triple prime equals some residual. Right. So again, the finite element method doesn't try to make this equal to 0 because it can't. Instead, it tries to make the weighted average residual equal to 0. So what we're going to do is we're going to take this whole thing and we're going to multiply it by a weighting function, and we'll come back to what that is, so times some weighting function, and we'll average it over the entire area. So we'll average it over the entire area of this computational domain. And it makes this quantity equal to 0, right? So this is the residual. This is us weighting it with a weighting function, and then we're integrating it over the entire area to get the average residual. So if I write this down, I get the integral over the area of f of xy times rho c d temperature d time plus d dx of minus k d temperature dx plus d dy of minus k d temperature dy minus g triple prime dA equals 0. So this is what we're shooting for, right? This is the residual. This is the weighted residual, I guess. This is our weighting function. And then this is us integrating it over the entire area. So let's take each of these terms and split it up into separate intervals or integrals. So we have, if we do that, the integral over the area of f times rho c and d temperature, d theta, d area. And we have our two conduction terms, so the integral over the area of f times d dx of minus k dt dx dA plus the integral of f times d dy of minus k times dt dy dA, and then finally minus the integral over the area of f times g triple prime dA equals 0. So let's start by looking at one of our conduction terms. And we're doing this so that we can convert at least this part of the equation from the strong form to what's called the weak form of the conduction term. So this conduction term, we'll write this again, is the integral over the area. So recall that our area is our computational domain. So we're integrating over this entire area of f times d dx of minus k dt dx times dA. If you think about this, this is a double integral. Right? I am integrating, this dA is an integral first with respect to maybe x and then with respect to y. So this is an integral that we can write like this, the integral of f times d dx of minus k dt dx times dx times dy. This is an inner integral where I'm integrating little strips with respect to x, and each one of these strips I might be integrating from, let's say, x west, so the left side, to x east. So the limits here are x west to x east, and then I'm integrating each of these strips to get my y integration. So if we look at this a little more closely, we can look at the x integration, and we can rewrite this using integration by parts. Right? So if I remember that integration by parts means that I can always, and when I see something like this, a function times the derivative, I can rewrite it in terms of the integral of the two functions and then the other function times the derivative of the first one. Right? So basically, if I just think about using the chain rule here, I would have d dx of, if I have the two functions, it would be f, and then I would multiply by minus k dt dx, and this is, by the chain rule, going to be equal to df dx, so the derivative of the first one times the second one, so minus k times dt dx, and then the second one, so this is plus f times d dx of minus k dt dx. So if I look at this for a second, this guy is what we were initially integrating, and then I can transform this into two different integrals, right? So let's go ahead and integrate every term here over x, right? So this then becomes the integral from x west to x east dx f minus k dt dx dx. So this is the first term integrated, equals the integral from x west to x east of df dx minus k dt dx dx. So that's this term plus finally the integral from x west to x east of f dx minus k dt dx times dx. So this is what we started with. This is exactly equal to this thing here, and I can express it in terms of these two other things. Right? If I look at this first one, and this always happens with integration by parts, this is an integral of an exact differential, right? So this just becomes then, f times minus k dt dx, evaluated at the two limits, so at x west and at x east. Right. So let's go ahead then and solve for what we were originally starting with. So we'll solve for this. This is, I'll just call this that. So this is equal to, I guess, this minus that. Right. So this is going to be f times minus k dt dx evaluated at x east minus f times minus k dt dx evaluated at x west minus the integral from x west to x east of df dx times minus k dt dx times dx. So if I look at this for a second, this guy right here, that is a physically meaningful quantity, right? That is actually equal to the heat flux in the x direction at x east, right? So this is, if I come back and look at this, this is the heat flux in the x direction at x equals x east, leaving at this point right here. And this guy, same thing. This is the heat flux in the x direction at x equals x west. If I take the minus, it's actually negative that. So this is the heat flux leaving here. Right? This is the heat flux at x equals x west. Right? So these two guys actually become the net heat flux leaving out of that strip. Okay, so let's write this again then. Now that we understand what those two terms are, we have the integral from x west to x east of f times d dx of minus k dt dx times dx. So this is what we started with, and we've now broken it into f times the heat flux in the x direction at x equals x east minus f times the heat flux in the x direction at x equals x west minus this new term, which is the integral from x west to x east of df dx times minus k times dt dx dx. Right, so we can substitute this back into our original double integral. So we get then that the integral over the area, so this is f d dx of minus k dt dx times dx is equal to the integral over y of this thing. Right, so this is f times the heat flux in the x direction at x equals x east minus f times the heat flux in the x direction at x equals x west minus the integral from x west to x east of df dx minus k dt dx times dx, and this whole thing integrated with respect to y. So let's split this into 3 different integrals so we can see what it looks like. So this is equal then to the integral over, so let's look at what this is actually, right? This is, if I look at this, this is integrating these little strips, right? So this guy right here is the integral, if this is the west side, and this is the east side, this is the heat flux leaving the east side, right? So this is now integrating all this eastern boundary, all this heat flux, weighted by the weighting function. So this is then the integral over the east side of f times the heat flux in the x direction at x equals x east dy. So that's this first one. This guy right here is this is the heat flux into, so this is the heat flux in the positive x direction, x equals x west. Here I'm integrating this guy all the way up the western boundary. So this is minus the integral over the western boundary of f times the heat flux x x equals x west dy. And then I'm left with, so minus minus is a plus, I'm left with this last term, which is the integral over the area of df dx times minus k dt dx and a d area. So this is the weighted value. This is the weighted value of the heat transfer out of this on the east side, and then this is the, if I take the negative of this, this is the weighted value of the heat transfer of this on the west side. So basically what I've got here is the net heat transfer leaving in the x direction. Right? If I were to do the same thing for the other conduction integral, right? So the one involving dy terms, I would get that the integral over the area of f times d dy of minus k dt dy, the area, I could break this up into the integral over the northern, so now I have a northern boundary and I'm integrating little y strips, right? So this is the integral over the north boundary of f times the heat flux in the y direction at y equals y north, minus the integral over the southern boundary, so here's the southern boundary of f times the heat flux in the y direction at y equals y south, plus the integral over the area of df dy times k times dt dy d area. Right? So if I substitute this and then also this back up into our original form of the weighted average residual function, what I'll get is this is the weak form of the conduction terms, right? So my conduction terms have basically gone from being an integral over the area of one thing to an integral over the area of this other thing, which I'm going to circle here. And then I'm left behind with integrals over the boundaries, right? This is basically the net heat transfer leaving the boundary. If I take this plus this, I have the net heat transfer leaving the boundary in the x direction. If I take this plus this, I have the net heat transfer leaving the boundary in the y direction. So totally I have the net heat transfer projected out leaving the boundary. So let's finish up then by just writing down what ends up being the weak form of our weighted residual equation. So we have the integral over the area of f times rho c d temperature d time, the area, plus the integral over the area of k times df dx dt dx. So this is what we got from the first integration by parts, plus df dy times dt dy, so it's from the second integration by parts, dA, minus the integral over the area of f times g triple prime dA. And then the second term we got by doing the integration by parts is this integral over the boundary of f times the heat flux normal to the boundary ds. Right, so this is, if you think about it, if this is our boundary, this is the heat flux, because I've moved it to the other side, this is the heat flux into the boundary. Right, so this is normal, and this is then the heat flux in the normal direction. And this is the weak form of our differential equation. Right? It's the same differential equation we were solving before. We've just taken what was an integral of the over the area of something that looked like k f times minus k dt dx. I'll get it right. Something that looked like f times d dx of minus k dt dx. And by integration by parts, we've turned it into this, and then part of that. We did the same thing for the one that looked like f times d dy times minus k dt dy. And this then is a form of the equation that we're actually going to work with when we do our finite element technique. So this is what we'll carry forward.